Welcome back. Section 7.2 is specifically on spanning trees. So, let's review. A spanning tree is a subgraph of a network that connects all vertices but has no circuits. So, let's take a look at the couple examples here. 1A. Is the following graph a tree? Why? This is going to be a no. Okay, we've got a couple problems here. I've got a circuit here. I've got a circuit here. I even have a circuit here. Okay. So, we're going to go ahead and find a spanning tree now. Remember, in order to find a spanning tree, we have to be able to connect all of these points, but not create a circuit. Also, remember, if we have 1, 2, 3, 4, 5, 6, 7 vertices, we need to have one less edge, which means we need to have 6. So, let's see. There's only one edge here that connects A to E. 2. This is a bridge already, so we cannot lose that. That's 4, 5, 6. And that's an example of a spanning tree. Okay. 2A. Is the following graph a tree and why? Okay. Do you see any circuits? I don't. Again, the fastest way to check this is check how many vertices you have. So we've got 1, 2, 3, 4, 5, 6, 7 vertices. And also count up your edges. We've got 1, 2, 3, 4, 5, 6 edges. Everything's connected. So yes, which means we don't have to do B. It is already a spanning tree. Okay. Some new concepts for today. Property number 4. We're going to learn a fantastic formula, and this one is called the redundancy formula. So anytime you have something that is not a tree, you can use this formula and it tells you how many edges you need to get rid of in order to create a tree. Okay, so if a network is a connected graph, so if everything's connected and your V represents your vertices and E represents your edges, then your edges should always be greater than or equal to the number of vertices minus 1. So again, like I said, we're going to talk about something called the redundancy formula. And this tells you the number of edges to remove. Oops, I need my pen here. This tells you the number of edges to remove to create a tree. And this formula looks something like this. your redundancy, you always want to take your edges minus your vertices and add 1 to it. And this goes along with this down here. Okay. If your redundancy comes out to be a 0, then your network is a tree. If your redundancy comes out to be greater than 0, it is not a tree. And whatever number you get represents how many edges you need to get rid of to create the tree. So, how do we find a spanning tree? So, your goal is to remove the redundancy edges to create a tree. In other words, to break up your circuits. And one thing we don't want to do is we do not want to remove the edges that are bridges, because remember, in order for it to be a tree, it has to be connected. If we remove a bridge, that disconnects my graph. So, example number 1. How many edges do I need to remove? So, the first thing we have to do is we have to calculate how many vertices do I even have. Okay, so I've got 1, 2, 3, 4, 5, 6, 7, 8 vertices. Edges, I've got 1, 2, 3, 4, 5, 8. Sorry, guys. I've got 8 edges. So you would use your formula. R equals. You would take edges minus vertices plus 1. So redundancy equals, my edges are 8 minus my vertices are 8 plus 1. That gives me a grand total of 1. So I need to remove 1 edge in order to create a tree. Well, now we need to find our circuit so we can remove one of those edges and answer question number 2, how many possible spanning trees exist in this graph? Well, my circuit's here, this triangle. So I can remove any one of these 3 sides, only one of them, remember, we just need to remove one of them. So this means I have 3, let me not write in highlighter, that's a bad idea, oops. I've got 3 different options. I can remove side HC, I can remove side CD, or side HD. So I would remove one edge from a circuit of 3 lines. The more circuits you have in your picture, the more complicated this becomes. So, let's take a look at our next example. How many edges do you need to remove? Again, let's use our redundancy formula. Why does it keep doing that? Okay, so First thing I need is how many vertices do I have? Well, I've got 1, 2, 3, 4, 5, 6, 7, 8. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 edges this time. So again, our formula is redundancy equals edges minus vertices plus 1. So 9 minus 8 plus 1. Okay. Well, that tells me I've got 2. I'm going to show you 2 different ways to figure this out. Method number 1 becomes very complicated. Method number 2, it can be easy, but it can also be tricky. So I'm going to give you both options. Please resort to any method that you feel is easier. I do not care. Okay, so method number 1. The first thing you want to do is find your first circuit. So the first circuit that we came up with here was CD, CH, HD, which was this triangle here. Okay. I also have a second circuit here. I've got this circuit down here. So in order to create a spanning tree here, I have to remove one of the edges from my purple circuit. So I'd either remove side CD. Okay. So I would either remove this, CH, this, or HD, this. Notice my circuit size for the second one. It's got 4. So I would either remove edge DE, which is this one here. I could remove edge EF. I could remove edge FG. Or I could remove edge GD. So I can remove side CD and any one of these 4 options, or I could move CH or any one of these and any one of these 4 options, or I can remove HD and any one of these 4 options. So that gives me a total of 12 different options. Again, I can just get that from counting. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, your second method to find this out. Think about it. We said circuit 1 had 3 edges. CD, CH, HD. Circuit 4. Circuit 4. Circuit 2 had 4 edges. Again, 1, 2, 3, 4. Well, if I multiply these 2 together, that tells me I have 12 different spanning trees. The next example is where it slightly gets complicated. Okay? Same concept here. How many edges do I need to remove? Well, let's see. We still have, nothing's changed here. Our vertices are still 8. 1, 2, 3, 4, 5, 6, 7, 8. Edges, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this one should look very, very familiar to the last one. Redundancy is edges minus vertices plus 1. So 9 minus 8 plus 1. 2 edges to remove. Again, we have to find our circuits. So the first circuit that they already give us, CD, CH, HD, this triangle again. Okay, those are all the options in that one. Our second circuit has gotten a little bigger now. We're here. This circuit has 5 edges. So you would think 3 times 5 like we did in method 2. We should have a total of 15. Well, look at my squares. I've got 15 here, right? There's 15. Well, let's take a look if I write this all out. Okay, let's see. My first edge is HD. That's this line here. My second edge is DE. That's this line here. And then EF. That's this line here. GF. That's this line here. And HG. That's this line here. HD, HD, DE, DE, EF, EF, GF, GF, HG, HG. Can anyone find my problem and as to why this is not 15? I will tell you this though, it's going to be 14. Okay, so let me give you that hint. There's 14 spanning trees. Take a look at the last column. We have to remove HD from this circuit, and then they want us to remove it again. We can't remove the same line twice. It doesn't work. So anytime you have 2 circuits that overlap, once you multiply the 2 numbers together, you're going to subtract 1. Okay, so let me demonstrate what I mean here in method 2. If I can get my mouse back up. Okay, so method 2. When we talked last, we said, okay, we take circuit 1, had 3, circuit 2 has 5 this time, so 3 times 5, that should give us 15. But because they share a common edge, we subtract 1. So 15 minus 1 gives us 14. So this is very, very important. I don't care how you need to highlight it. Do not forget that. Only if they share a common edge do you need to subtract 1. Okay, so we've got some practice problems, and then you guys can start your homework. Spanning tree practice. Find the total amount of possible spanning trees. How many circuits do we have in graph number 1? Well, I only have one circuit, and it's got 4 edges. So there are 4 spanning trees. In graph number 2, how many circuits do I have? Let's see, I've got one circuit here with 4. And I've got a circuit here with 5. Four times 5 is 20. Do they share an edge in common? No. I have 20 spanning trees. Example number 3. I've got a circuit here with 4. And I've got a circuit here with 3. So 4 times 3 is 12. Do they share a line in common? Absolutely. They share this line in common. So we need to now subtract 1. So this one has 11 spanning trees. Okay. 4. Now be careful. You want to find the circuits that share anything in common first. Okay, and then do those and then multiply the rest in. So, in this one, I've got, let's see, I've got this circuit of 3. I've got this circuit of 3. I've got this circuit of 5. And I've got this circuit of 4. Now, 4 and 5 share a point in common, but not an edge, so that's okay. But these two over here, they share this line in common. So we need to do these first. So this is 3 times 3, which is 9. Don't forget to subtract 1 for that overlap, so that's 8. Now we take that and multiply it with how many this has and how many this has. So my final answer is 4 times 5 times 8, which gives me 160 spanning trees. Okay. 5. Here's 3. 3. This is 5. Okay. 1, 2, 3, 4. 1, 2, 3. Okay, so 3 and 5 share a common edge. 4 and 3 share a common edge. So we need to do these two separately and then multiply the two answers together. So we've got 3 times 5 is 15, minus 1 is 14. So 14 for this top part. And 4 times 3 is 12, minus 1 is 11. And then finally, 11 times 14 gives me 154. Two more examples. Okay. 6 and 7. We've got a circuit of 4. We've got a circuit of 3. And we've got a circuit of 1, 2, 3, 4, 5, 6. They share a common vertice, but none of them share a common edge, so we just multiply. 4 times 3 times 6, 72. Finally, number 7, got a circuit of 4. Got a circuit of 1, 2, 3, 4, 5. Got a circuit of 1, 2, 3, 4. Circuit of 1, 2, 3, 4. This circuit shares an edge in common, so we need to calculate that first. So 4 times 4 is 16, minus 1 is 15. So then 15 times 5 times 4. 300 spanning trees. Okay, your homework tonight is going to be page 266 in your book, numbers 11 through 18 all. Okay, please do not skip anything. You need to be doing all of these problems tonight. Good luck, and I'll see you back here tomorrow.